Welcome back to the lectures on acidity constants and acid-base reactions of organic chemicals. In this little sub-lecture, we're going to talk about the partitioning behavior of chemicals that have exchangeable protons. So first we're going to talk about the pH dependent of the solubility of a compound. Now when we began this whole course, we started off by talking about vapor pressure, right? But there's really no point in talking about vapor pressure because chemicals that are ionized, so the anion of the acid or the protonated base that's positively charged, they can't evaporate into the gas phase, period, right? So there's really not much to say in terms of vapor pressure. So let's talk about solubility. Solubility, as we know, is the equilibrium partitioning of a compound between the pure liquid phase and the water. And the solubility is intrinsically linked to the activity coefficient, and Renee Schwarzenbach will never let you forget it. So the solubility of the neutral form and the activity coefficient of the neutral form of the chemical depends on, as we've already discussed, its size, polarity, and hydrogen bonding. But the intrinsic solubility of this uncharged form of the chemical is not affected, right? The intrinsic solubility of this neutral form is not affected by the acid-base reactions. As long as the chemical stays in the neutral form, everything that we've already learned in this class still applies. But when the compound either loses a proton and becomes negatively charged or gains a proton and becomes positively charged, the apparent solubility will increase. So here's an example. As the pH increases for an acid, down here at low pH, it's all protonated, it's all in the HA or neutral form, and its solubility is flat. Doesn't change. But then when you start to approach the pKa, which in this figure is right here, you start to take some of these protons off and you get some of the A- form. A-. Ooh, that's bad. Anyway, A- form. So as the pH increases, you're pulling off some of those protons, you're getting the A- form, and this A- form, it's an anion. It's really, really, really soluble. So the total solubility, the total amount of HA plus A- that's in solution just keeps going up and up and up and up. And it only levels off when you get to a place where this A- precipitates out as a salt because it runs into something else in solution, like maybe a sodium cation or something, and the two get together and form a salt and fall out of solution. Otherwise, this thing just keeps going. So the apparent solubility of the compound does seem to change. The intrinsic solubility, again, of the HA form does not change. The intrinsic solubility of the HA form does not change, but the apparent solubility of the compound does. So we've already talked about the fact that alpha represents the fraction of the total amount of the compound that's in the neutral form, and we know we can calculate alpha using this formula where we just need to know the pH and the pKa of our chemical. So the solubility of the total chemical, HA plus A-, CW sat total, is equal to the CW sat of the neutral form divided by alpha. And for a base, because for a base the fraction that's in the neutral form is 1 minus alpha, the solubility of the compound total, B plus BH plus, is equal to the solubility of the neutral form divided by 1 minus alpha. So that takes care of solubility. What about Henry's law? Well, we can safely assume that the ionized form cannot volatilize because ions just don't go into the gas phase. So we could calculate this thing that we call the distribution coefficient, DAW. So instead of KAW, which is an equilibrium constant, we're going to calculate a distribution coefficient, DAW, which applies both to the neutral form and the anion here, if we're talking about an acid. And that would be equal to alpha times the Henry's law constant. So this is the Henry's law constant with units, pressure units. And then if we divide by RT, we get the dimensionless Henry's law constant here. But either way, you just multiply it by alpha, and you can get the distribution coefficient for this chemical partitioning between air and water. For a base, the fraction that's in the neutral form is 1 minus alpha. So the distribution coefficient for a base is 1 minus alpha times the Henry's law constant. So that's not too bad. And you can probably guess where we're going with this now. The octanol water partition coefficient can be treated in a similar fashion. we will pretend that the ionized form does not partition into the octanol. It can, but we're going to pretend that it doesn't. Observations suggest that the neutral form is much more attracted to octanol than the negatively charged form. That makes sense because things with a negative charge are very hydrophilic. They love water. They want to stay in the water, whereas neutral compounds are much more hydrophobic. They would much rather go into the octanol. So this is a reasonable assumption, to assume that the charged form does not partition into the octanol. And therefore, we could do the same thing that we did before. We could calculate some sort of distribution coefficient for partitioning between octanol and water of HA and A minus, and that would just be the intrinsic KOW multiplied by alpha for an acid. For a base, our distribution coefficient would be 1 minus alpha times KOW. So that's pretty straightforward. Sorption is much more difficult, and this is partly why I put the sorption lectures first before we did the acid-base chemistry in this class. So we talked in the sorption lecture about the fact that acids and bases, because they can have a charge, might sorb onto surfaces such as minerals via an electrostatic attraction, right? So many mineral surfaces have an overall net negative charge. So if you're a base floating around, you pick up a proton, you have a positive charge, suddenly you become very attracted to the negatively charged mineral surface. So we know that sorption is going to be a function of the big three types of intramolecular interactions: van der Waals forces, polarity, and hydrogen bonding. But now that we have a charged species, we also have to consider these electrostatic interactions. And there's also a potential that we could form covalent bonds between the chemical and something like natural organic matter. So again, we're going to use the letter D as a distribution coefficient to avoid any confusion with K, capital K, which is an equilibrium constant. And we know that at ambient pH, natural organic matter is negatively charged, right? Because it's got all those carboxylic acid functional groups. And so those are mostly deprotonated, and the thing has an overall net negative charge. And for this reason, natural organic matter acts as a cation exchanger. That's what we talked about in the sorption lecture. So negatively charged species will sorb more weakly to natural organic matter. They're not going to be as attracted to it. And in fact, they're going to be sort of repelled by it. So sorption of negatively charged species can, for the most part, be ignored. Okay? But positively charged species will sorb more strongly to this natural organic matter than the negatively charged ones. And sorption due to these electrostatic interactions is usually going to be fast and reversible. It's sort of on the scale of like a proton exchange reaction, which is a similar idea. It's an electrostatic kind of thing. So they're usually fast and reversible unless you start to get some covalent bonding, in which case, then the sorption becomes completely irreversible. So for acids, for example, we could define a distribution coefficient. Instead of KOC, we could have DOC. And we could think of this as the concentration of the neutral form in the organic carbon plus the concentration of the acid form in the organic carbon, the anion form in the organic carbon, divided by the concentration or mass of the neutral form in the water plus the concentration or mass of the anion in the water. So we know the relationships between AW and HA and A minus in the water and in the octanol because we know how to calculate alpha. So we could calculate a distribution coefficient for our chemical. We'd have an equilibrium constant for the HA form. And that's probably what you're going to look up in a textbook is the equilibrium constant, the KOC value for the neutral form. We could multiply that by alpha, which is the fraction of the chemical that's in the neutral form. And then we might, maybe under some circumstances, be able to look up an equilibrium constant for sorption of the anion to organic carbon. Now, most likely we won't be able to find this. But let's say we could. Then we would multiply that by 1 minus alpha because for an acid, 1 minus alpha is the amount of mass that's in this negatively charged form. So we're basically calculating a weighted average of these two equilibrium constants based on how much of the chemical is in the neutral form and how much of the chemical is in the charged form. Now we know that the equilibrium constant for sorption of the neutral compound to the organic carbon should be much, much greater than the equilibrium constant for absorption of the negatively charged form to the organic carbon, right? Because we know that organic carbon is generally a pretty nonpolar phase that likes to absorb nonpolar things, and we also know that to some extent OC will have a negative charge on it and therefore will repel negatively charged anions, and so K of the neutral form is much bigger than K of the negatively charged form. So you can usually just ignore the absorption of the negatively charged species. You can usually just ignore all of this. Don't worry about it and just worry about this part of the equation. Okay? Now what about bases? Bases are tricky. So here's an example absorption of an acid. So here's two acids, 2,4,5-trichlorophenol. It's got a pKa close to 7. And then here's pentachlorophenol, pKa close to about 5. And you can see that the absorption at acidic pHs, this is all protonated, and the absorption is sort of constant. The distribution coefficient is constant here. It doesn't change much until you start to approach the pKa, which is here at 7. Right? Here's your pKa. As you approach the pKa, some of the compound starts to become deprotonated and negatively charged, and therefore it's not absorbing as well, so the overall absorption is plummeting as you get to more basic pHs, because more and more of the chemical is in the more and more of the chemical is in the deprotonated and negatively charged form, and it's just not absorbing very effectively because it's negatively charged, and it doesn't really like to be around natural organic matter. But if you do the same kind of calculation for pentachlorophenol, what you see, again, so the pKa is right around here. And again, you see at very low pH, you get a pretty much constant flat DOC, distribution coefficient for organic carbon partitioning, not dissolved organic carbon. Very confusing. We get a pretty constant distribution coefficient here at low pH. And then as we get to higher pHs and some of the compound becomes deprotonated, it becomes negatively charged. But the difference is that pentachlorophenol has 5 chlorines, pentachlorophenol versus trichlorophenol. So pentachlorophenol, even the anion of pentachlorophenol, is still a big-ass hydrophobic molecule. And so even the anion has measurable absorption to organic carbon. So this levels off at some fairly high value of the distribution coefficient, because pentachlorophenol is just so hydrophobic that even when it's negatively charged, it still has some affinity for the natural organic matter. Absorption of bases, much more difficult, more complicated. Absorption of the cationic form of the base is going to be quite favorable because it's going to want to absorb to these negatively charged sites on things like natural organic matter and even many mineral surfaces. But we know that if we're talking about an electrostatic attraction between a positive charge and a negative charge, there's only so many negative charges, right? And therefore, we have a limited number of absorption sites. And we remember from the absorption lecture that when we have a limited number of absorption sites, we have an isotherm that looks like this and levels off, and it's a sideways L. And L is for Langmuir. So we have a Langmuir type absorption isotherm. That's great. So we know that the absorption isotherm is going to be nonlinear. The problem is that it's going to be a strong function of pH. So this, here, in this plot, we're expressing this as a function of CW, right? And this is CS. Ooh, she's getting good. Okay, but here we're looking not at CW and CS, but we're looking at absorption as a function of pH. Right, so as a function of pH, you get the most absorption at sort of this intermediate pH, right? So this is absorption of quinoline onto aldrich-humic acid. So at very low pHs, the quinoline is protonated and in the neutral form, but so are all of the sites on the natural organic matter. So any attraction between the two is really just a hydrophobic type interaction. But there's some optimal pH where the quinoline is still neutral, but the natural organic matter is negatively charged, and you can get some electrostatic attractions. And then as you get to really high pHs, you get to the point where the quinoline is... So let's try this again. The absorption of quinoline is shown here. It's a base, right? So at very, very low pHs, the quinoline is positively charged. Okay, so it's protonated, it's positively charged. But the problem is all of the carboxylic acid groups on the natural organic matter are also protonated, and that makes them neutral. They have no charge. So you have a positively charged thing here trying to absorb onto a neutral surface. It's not that favorable, so you don't get a huge amount of absorption. Over here, the pH is quite high. The proton has been pulled off of the quinoline. The quinoline is neutral, and the natural organic matter is negatively charged. So a neutral compound trying to absorb to a negatively charged natural organic matter, it's okay. You know, there's some intrinsic amount of absorption here, but it's not huge. But in between, there's some maximum here where the quinoline is positively charged and the natural organic matter is negatively charged, and there's a big electrostatic interaction. And it occurs sort of somewhere in the middle here. So the pKa of the quinoline is right around here, right around 4.9. And that turns out to be right about where you get the maximum absorption. But it depends not just on the pKa of the quinoline, but it also depends on all the pKa's of all those carboxylic acid functional groups in the natural organic matter. So the take-home message is that absorption of bases is really, really tricky. And if you do need to deal with that, then you have to really take your time and think about it. You can't just apply some of these very simple absorption isotherms that we learned in the absorption lecture. You're going to have to think really long and hard about pH, about the pKa of your compound, about the types of minerals that are present in your aquifer, and also about the types of organic carbon that are available in your aquifer. So problem 8.1 and problem 8.2 are both available as example problems. They are listed under resources, under homework and practice problems, under practice problems, and I've also made videos for them. So problem 8.1 is representing graphically the speciation of a couple of chemicals. Here's a phenol, which is an acid, and an aniline, which is a base, as a function of pH. And you have to estimate the pKa values using the Hammond equation. And then problem 8.2 is the speciation of tetrachlorophenol in a dense fog. So that's another partitioning type question. So go take a look at those, and hopefully they will help you understand what's going on with some of these questions about partitioning of acids and bases.